So what we showed is this inequality, that phi of f of x is minus phi of t minus p times of f of x minus t is bigger than or equal to 0. So if I integrate throughout, you're going to get phi of f of x minus integral of phi of t minus b integral of f d nu, okay, and plus, yes, you're right, so you're going to get t times mu of omega, because if you integrate it, so t is like a number, so it will come out, but mu of omega is 1, so it's be dx. But if we recall, we set t to be the integral of f d nu, so this means that these two guys will go away, and you get, you call this bigger than or equal to 0. So it's equal to omega phi composition f minus phi of t, but the t is the integral of f d nu multiplied by what do you say? Mu of omega. Okay, but the mu of omega is 1 actually. So this is greater than or equal to 0, and hence you get what you want. This is one of the most frequently used resultant. Why is the case? Let's do some few things based on it quickly. Let's begin with something. So you can prove a hell lot of interesting things based on this. Very interesting. Think about it. So consider this function phi of x equal to e to the x. So is it convex? In other words, you differentiate it 2 times, it's always non-negative. So it's convex. So if it is convex, what does this inequality is telling you? That e to the integral is less than or equal to, okay, is less than or equal to what? Integral of e to the f d. Just get an interesting conclusion. E to the integral is less than or equal to. By the way, I can treat this integral, if I treat, for example, mu to be the probability measure, okay, then I can treat this inequality as that phi of the expectation, and f is say integral, say x, where x is an integral random variable, is less than or equal to expectation of phi of x, okay, for any convex function. Okay, and what does this mean? So and hence you do the same thing. So this means that e to the expectation of x, for example, take the same function, is less than or equal to expectation of e to the x. Okay. Take another function, say for example phi of x equal to x square, and use this inequality. So what does this show? So expectation of x square is less than or equal to expectation of x square x. Get it? Or I can say you have it. Okay? And think about it. What does this show? So if something is a square integrable, so its first movement must exist actually. Is it? First movement must exist. Even you can, so instead of taking a square, if I take absolute, So what are you going to get? Absolute of expect. So in other words, you can take many things coming out of this very simple inequality.
The Riemannian sense may be true or given by.
Riemannian sense may be true. Make sure that the assumptions are true.
Probability of space should be 1.
That's what is the key thing, that you have the assumptions are true, and yes, you can also use them in Riemannian case. By the way, you can also show that is, using the thing, give it a thought of y, is that similar kind of inequality is even true for the conditional expectation. So in other words, phi of the expectation of x given g, if g is some sigma field, is less than or equal to expectation of phi of x given gx. Okay. Because this integral is, in other words, this is also a kind of Hilbert integral. You can write it out. So there are many consequences of this inequality. Very interesting inequality. Quickly take omega to be a finite set. Okay. And assign each of these points probability 1 over n. And the mu of omega is 1. Consider a map f from omega into R such that f of pi is some number xr. Okay. Then what would be the integral of f d nu? The integral of f d nu is going to be simply
Summation xi.
equal to 1 to n f of pi multiplied by
Indicator function.
measure of this each of the points pi at. Agree? We have this. And by the way, what does this mean? This means that you have x1 plus x2 and plus xn and everything divided by n. Okay. Thus, if I use Jensen's inequality, then and take phi to be exponential, the same exponential function, then what does this shows is that e to the integral f d nu, okay, is less than or equal to the integral of e to the f du. Okay, and e to the f du is going to be what? It's going to be equal to, can I say, sum I equal to 1 to n. So you see, what I'm heading is basically that a very elementary inequality can be proved very easily through what you call Jensen's inequality. So it's not just they have, this inequality has consequences in probability, but everything. Alright, can I say this? Okay. Can I say this? In other words, this would be what? So if you are integrating f d nu is basically f of pi and multiplied by the probability, so you can do the precisely same thing here. Okay. By the way, on this side, what do you have? What this integral is equal to? So this is equal to
e power
xi I equal to 1 to n and everything divided by n and raised to e. Okay? Now set yi to be e to the xi. Okay? Log of yi is xi, right? And replace it. So you get what? You get e to the sum of 1 to n log of yi's, right? And this is less than or equal to
divide by NBO.
I equal to 1 to n yi and everything divided by n. Yes, divided by n भी हमें दे सकते हैं, but I can
root.
make it nth root as well. Okay? And then this would be what? So this would be the product basically. Okay? But the product will turn into e to the log yi to the n. So e and log will go away. Okay, so you're going to have a y1,
Sum to product.
y2, sum of them, product will
Product.
yn
And through.
nth root is less than or equal to I equal to 1 to n. Okay, so be careful about the notes that I'm going to send you. So that's a mistake in it. Okay. I'm making notes, so you can find mistakes anywhere, typos anywhere. So what does this inequality is showing you that the geometric mean of n of the n numbers is less than or equal to the arithmetic mean. Okay, so something that we know from our basic mathematics actually, the geometric mean is always less than or equal to what we call the arithmetic mean. Okay, it's true here. Anyway. Keep it 5 minutes. Everybody inequality and give you other. So, do you remember that? Did we prove these Holder and Minkowski inequality in our function analysis courses?
Yes.
We proved them. We just use them. We proved them.
We proved all.
Okay. I remember that we did it.
सर कर लीजिए हमने जी सर रिजल्ट में पढ़ी
Anyway, so you can also prove the Holder's and Minkowski inequality based on an argument that is based on Jensen's inequality. So I'm just giving you a sketch, just a sketch. So what does Holder's inequality says? Holder's inequality is that if you have two measurable functions, in other words, I have a measure space and two measurable functions, so it's maps from x into 0 to infinity, then the integral of the product of x d nu is less than or equal to integral the pth norm basically, LP norm. We haven't defined LP spaces, but yes, we will do it. Less than or equal to pth norm of f times the qth norm of g. Okay, 1 over q.
So
That's
g power
Holder's
q.
inequality, huh?
G power q.
G power q, yes. G power q and this. And by the way, similarly, you can, for the same, you can also write Minkowski inequality. I'm proving one, one you can think about doing yourself. You can read the proof for yourself. The Minkowski inequality is about the sum. So what this is basically saying us that the L1 norm of Fg is less than or equal to LP norm of F times LQ norms of what do you call G. Okay.
So this is condition on PQ, right?
Oh yes, yes. One over P plus one over Q
Q is
must be 1. There must be convex conjugates. There must be conjugates. Conjugate exponents. And also P should be between 1 to infinity. Okay, so it must be in convex domain. How can I show all this? Without loss of generality, assume that the integral of f, or maybe you can also consider this as a case actually, that this integral and the qth raised integral of g, the both are 1 actually. If they are not 1, I can normalize it and I can turn it into a 1. In other words, here's the thing. If this guy is not equal to 1, then I can somehow divide by magnitude and multiply by magnitude. I can turn it into a 1 actually. Okay, it's not a big deal. So let's assume for this case first actually. Let's assume that they are 1. Okay. And if they are not 1 actually, so in other words, they are non-zero. Both are non-zero. GQ are non-zero. So if they are non-zero, then I can write a function who's going to mimic or who's going to give you this inequality. So let's write f bar, for example, that is equal to f over
Norm of x.
the norm of x, the LP norm.
1 by
Okay, and take the g bar to be
same.
g over gq
1 by
and 1 over q. Everything is on that side. Okay, so in other words, if they are 1, fine. If they are not 1, I can create a functions for which this is true actually. You can think about it. If I raise it to the p and integrate it, then the integral is equal to 1. And similarly, the integral is equal to 1. So, we can do this. Okay. What if the both are 0? Or at least one of them is 0, then the inequality trivially holds. So in all cases, argument 1. So what I would like to claim? My claim is this.
integral of
I would like to show that
integral.
what you call this inequality holds. Sometimes this inequality.
Jensen.
I forgot the name of the inequality. A to the p over p plus b to the q over q. Okay, so in other words, for any two numbers,
Right.
okay, you can have such kind of an inequality. So what is
Replace A by F bar and B bar.
so take a and b to be any number from 0 to infinity. Okay, so if this is true, can you see that we can get this as well? Okay.
F bar.
So let's just show first this inequality. Quick. The extreme cases are easy. So if it is A, if A and B are 0 or infinity, the inequality is true. So the interesting case would be that when A and B are, especially the A is in, A is something in 0 to positive infinity. Okay?
Convexity of E.
Both A, both values in positive infinity. Okay? And now take omega to be x1, x2. I could have proved this as lemma. Okay, something such that mu of x1 is 1 over p and mu of x2 is 1 over q. Because this p and q are the same that you have fixed arguments, then I can use Jensen's inequality. So Jensen's inequality is going to give me what? Jensen's inequality,
The exponential function.
exponential of the integral
It is the
du is less than or equal to
integral of E power f.
integral of e to the f and
dv.
dt. And the integral of exponential is going to be, okay, maybe I must fix actually that take f of x1 to be some s and f of x2 to be some p. Obviously, it's going to be some real number. Okay. Then this inequality is showing what? This inequality is, so what would be this integral? So this is going to be s over p plus
T over Q.
p over q, and this is less than or equal to e to the s over p plus e to the t over, what do we say, q. Okay. And take a to be what? Take a to be s over p and take b to be e to the t over q actually. So do we have the inequality?
Yes, sir.
Okay. Do we have the inequality? So you have e to the s over p, which is a, and e to the t over q, which is b, less than or equal to, what are we going to say? So a to the p, because if I take the pth root, so you're going to have a to the p over p plus
B to the Q.
b to the q over q. So the inequality is true. Okay. So we should then prove this as a lemma. Now if this inequality is true, we get star. Okay, finally.
Young's inequality. Yes, Young's inequality.
I'm sorry.
This inequality to be proved is Young's inequality.
As what?
Young's inequality.
Young's inequality, yes.
We did it already.
Young's inequality. That's what I was forgetting. By the way, be very careful about Young's inequality because this is basic Young's inequality, but there is also called popular. It's a very popular Young's inequality, but it's about the convolution actually. That if you have a convolution, particular norm of a convolution, then it's something like similar. There are many Young's inequalities actually. So consider this now. So what would be, okay, finally, consider this now. FGD nu, okay, FGD nu is less than or equal to, so this is like the product actually, is less than or equal to integral
If